So this is the final exam. I will be talking about another exam that was offered in May of 2022, but just so you're aware of this, 2020, 2021 being COVID years, the final exam was online. 2022, on the other hand, was sort of the distant end of COVID, and I'm hopeful that at the point where you're taking the course and looking at this, that means that we don't have uh, well, we don't have COVID, and we have in-person lectures, and everything is the same as it was, say, in 2019. Final exams cover the whole course, and it's not hard to see what we emphasize. You just need to look at a few old exams, and if you do that, you'll look at 2020, 2021, 2022 in this case, and you'll see what we've covered. One thing to note is that there's not much change. So despite the fact that 2020 and 2021 were online, and the courses were offered in slightly different ways in each year, generally we've tried to sort of maintain a consistency in terms of expectations. So the final exam doesn't change significantly. And I kind of want you to make sure that you sort of look at it from that kind of lens. So how does this compare to past years? I think final exams mostly tend to look about the same. Question 1 was a projectile motion. A projectile breaks up 7 seconds after launch, and it hits point P. Or at point P, it breaks up into 3 components. So point P is right there. A, B, and C, mass of 10 kilograms, 30 kilograms, and 20 kilograms respectively. And at that point, B and C land on hills of coordinates shown in the diagram. Pieces A, B, and C remain airborne for TA 2.87 seconds, TB 32.1 seconds, and TC 6 seconds respectively after the explosion. And you're given sort of a set of positions for A, B, and C, for B and C, not for A. And so if you look at this, you see that that's there for C, there for B, and you have the initial position there. You get a 3, 4, 5 triangle, and you should recognize a 3, 4, 5 triangle at this point. You're given all of this motion. It's very complex, and I understand that, but it's complex 2D motion, and it's going to combine some ideas of projectile motion and momentum. Pre-explosion, V naught is 125 meters per second. Time of flight is 7 seconds when it explodes. A mass is 60 kilograms, and then you're given the final positions and times. So if you do that, you can substitute in those expressions and get rid of x naught, y naught, because those are 0. Vx naught, Vy naught, on the other hand, are given, and you have to use the 3, 4, 5 triangle. The difference is that x is horizontal motion, so there's no gravitational acceleration, and y is vertical, and so you'll have gravitational acceleration. So you're given the final position, P, is 525 and 459.7 meters. So the distance that it's traveled, and you can figure out Vx at the time of explosion, it's going to be 75 meters per second. That's going to be constant because it doesn't change with time. Vy is going to equal 31.3 meters per second because of gravity. If you find what the initial velocity to collide with the bird, well, that requires a velocity of 184.5 meters per second. You want it at the same position as the bird. There you go. Evaluate the coordinates of the valley at which A lands, so 4 marks for that. Again, you're just using here projectile motion expressions. So there and there. And you can calculate that to be 45.95 meters per second and VYB to be 190.5 meters per second. And you get all of the positions, analyze the motion of C. C parameters are given. Sorry, both of these are just giving you parameters. And you know that this is a conservation of momentum, and Vxa and Vaya are given. You can see that those are pretty high numbers, very high. These are kind of mawkish numbers. 678.8 meters per second and 947.7 meters per second for this to happen. And that's just by conservation of momentum, where you've seen these problems here. It's a little bit more complex because instead of splitting into two parts, it's splitting into three. And when it splits into three, you got to sort of consider everything. But you have enough information to solve for all of those positions. Analyze motion, you get XA and YA. So you calculate 2473.2 meters minus 2300.5. Calculate the distance to the location and the distance from where we're sort of setting this up for, and it ends up being, surprise, surprise, 0 meters, and there you go, you land right on top of it. Generally, this is covering particle kinematics and kinetics, or kinematics and kinetics, actually, so it's covering particle momentum. It's really wrapping up the first half of the course. Second one is a motion, and again, you have a lot of different ways of solving these problems. You got to just be aware of them as you look at them. At the instance shown, bar AB, so bar AB over here, is in vertical position, has an angular velocity of 10 rads per second counterclockwise. So it's rotating like this, omega, and it is slowing down at a rate of 2 rads per second. Bar BD is pinned to the circular disk, which can rotate about a fixed point E. So I know one other thing. I know that this is going to tell me this is the direction, and that this is sort of the limits of the direction. It can only go vertically at that point. It has to go normal to the line from E to D. So at this point, we have a bit of information. And what we want to do is determine the point, or the acceleration point B. So again, we know the velocities at B and D, and we know the directions. And we have all of that information from the previous slide. Velocity B is acting to the right, velocity D is acting downward. Omega BD is equal to velocity B divided by LBC, the length of BC. And you get 8 rads per second clockwise. Velocity of D is just going to be the length of CE from the center of the wheel to omega BD, which is just going to be 8 rads per second, which we just calculated, and that's 4.8 meters per second down. I'm not putting signs here, I'm just putting directions. Omega DE, which is the other component, is just going to be velocity D divided by LDE. Accelerations, acceleration B equals acceleration A plus acceleration alpha AB crossed with the distance minus 0.2 meters J minus omega AB squared RAB. So putting all the terms in, calculating, you get the acceleration B, which is equal to minus 0.4 meters per second squared I, 20 meters per second squared J. Terms are good, everything is there, you just have to recognize what the system is. So in terms of final solutions here, omega BD minus 8 rads per second. VD is minus 4.8 meters per second. And omega DE is minus 24 rads per second. Everything is rotating clockwise. So we then take our relative velocity terms. Acceleration D equals acceleration B plus acceleration of D with respect to B, substitute in the terms, and recognize that we have all of these expressions here. So when you're sort of looking at this from that perspective, you have the tangential acceleration and the normal. And remember that, again, I didn't stress it too much on the last slide, that this is only true when you have planar motion in the xy plane. You have to do it a little bit different in each expression. Substituting in numbers, I get an expression in terms of alpha BD, and I can put those values in. Same thing with acceleration of d with respect to point E. Do the same sort of calculation, get another set of numbers. The difference is now I have two equations, 1 and 2, with two unknowns. Acceleration d equals acceleration d. It can never change because it has to be the same at a point. Substituting in terms, equating, the I terms. So here I'm taking these two terms here. And then for the second part, I'm taking j over here. Substitute in, solve for everything, and a little while later, you get two clockwise rotations, 305.6 rads per second squared and 736.8 rads per second squared in the z direction clockwise. This is a problem that covers rigid body kinematics. And it's really just an application of everything. It's not a bad problem in terms of complexity. It is a challenging problem because you got to keep everything in mind. So it's helpful that you spend a little time to look at how we do these things. And there are a number of lectures that I certainly would encourage you to take a look at. Moving on, circular spool of mass 15 kilograms has an inner radius of 0.4 meters, outer radius 0.9 meters. Its radius of gyration is 0.7 meters. The spool rolls without slipping on its inner hub along a rod slanted at 30 degrees above the horizontal, and you can see all of this in the figure. Rope is wrapped around the outer rim, and a tension of 65 newtons is applied, acting normal to the ramp. At the instant shown, the spool has an angular velocity of -5 rads per second. So you're given all of that information to work from. Positive direction is also defined here as counterclockwise, as is usual. A little bit different in terms of how we define the axes, but x and y are shown here with the positive direction of rotation, and it follows the right-hand rule. Determine the velocity of point A, acceleration b, and express your answer in the xy coordinates as shown. You can do that by just calculating velocity of A, 5 rads per second, 1.3 meters, and acceleration of B is just going to be the normal acceleration, and you can calculate that and get all of the information. Alternatively, you could use a vector solution, and I actually recommend those as long as you're comfortable with it, and just substitute -5k rads per second and a positive 1.3 meters j. Notice, of course, that the xy coordinate is in the direction of motion. So you get velocity of A, acceleration of B. There you go. Determine the angular velocity alpha of the spool at the instant shown in the diagram with positive angles measured in the counterclockwise direction. Okay. First thing, moment of inertia, always calculated, 7.35 kilograms per meter squared. And from there, you can do the sum of forces in y, which equals 0, sum of forces in x. You'll notice that the friction direction is acting up. So it's in the negative x direction. You've got the weight component that's also acting there. You'll know that you have an acceleration in g in the x direction, and ig alpha is, sum of moments is ig alpha. So the moment from P is causing a counterclockwise moment. The moment from friction is causing a clockwise moment, so that's negative. And all of this is going to be 7.35 alpha. So the normal is 192.4 newtons. You don't really need this. And I just want to sort of highlight this. This is a question I often get during lecture and on the various discussion boards, Piazza in the past. I don't know what we'll be using this year. But why did I choose this direction? Because I assume that the wheel will start to rotate counterclockwise because of that force, and that alpha is going to be acting in that direction, and I'm putting friction in that direction. Solve the two equations and get alpha equals 2.98 rads per second squared, and then friction, which is equal to 91.49 newtons, acting up the ramp. It's a negative value, but I have correctly guessed the direction. Alternatively, I could recognize that this is no slip, and because it's no slip, I can use point B as a point to do the rotation. Now, usefully, I would calculate Using the parallel axis theorem, my I about B, do alpha about that point. All of the terms pretty much disappear, except except for the P moment and also the weight component that is acting in the x direction. So putting all the terms together, substituting in, I get, no surprise here, the same answer. And I get the same answer of counterclockwise alpha of 2.98 rats per second squared. Rigid body kinematics, kinetics, and chapter 5. Bollard throws a ball weighing 80 newtons and radius r ball of 150 millimeters along a floor with a forward velocity of 15 meters per second and a backspin of 12k rats per second. So in this case, you're drawn or shown on the diagram what omega naught looks like. You have a sphere, I sub g, which is equal to 2.5 or 2/5 mr squared. That was given to you, and we will often give you, aside from long slender rods, and long slender rod generally is the one we give. There's another one I'm offhand, I can't remember. G equals 9.8 meters per second squared. All of the information is there, standard or direction. All of the given values are there. You can calculate. Now this is a funny problem because it's SI units and we gave you a weight, and so you have to calculate the mass, and it's 8.1549 kilos. Moment of inertia for the sphere, put in the terms, there you go, 0.0734 kilograms meters squared. Again, principle of impulse momentum, you have the initial linear and angular momentum of the system. You have the external moments, or forces causing moments, and then the final momentum of the system. Angular momentum at the ball at time 0, ig omega naught. You substitute in terms, nt minus omega t, or weight, and normal equals weight, and 80 newtons, and the force of friction is 12 newtons. Linear impulse momentum principle, you substitute in terms, all the terms are there. You divide by mass, and once you do that, you end up with an expression for V1, the final velocity, in terms of time. And so there you go, 15 minus 1.472 t. At the moment T1 is which is where the ball will start rolling without sliding. Angular impulse momentum. You have ig omega naught minus force of friction T, which is the moment, times r. So that's the angular momentum or angular impulse delivered, minus ig omega 1. So you have T, which is you calculate in the previous part of the problem. Substitute all of the terms back in, and once you do that, you end up with omega 1, which is 25 or 24.52 T minus 12. These sort of work. And slipping stops when the velocity is equal to omega 1 r. Substitute both together, calculate t, and you end up with 3.3 seconds. And the velocity at time 1, not so hard. You've already got all the information there. You substitute in your t, which you calculated is 10.2 meters per second. And that covers rigid body impulse and momentum. This is one of the problems that we have. It often looks more difficult than it is. These are two masses that are connected by an inextensible cable which passes over a pulley of radius RC. What is the critical driving frequency of the block B? So you have block B, which is up at the corner here. You have the mass, which is attached, M1. You have the mass, M2. You have a couple spring constants. And one of the things you have to do with this is not to get overwhelmed with the drawing, because all you really want to do is write an equation of motion. And that equation of motion is going to be partially driven by the spring on mass B. And you can say that's xb minus x1. You get an equation of motion for that, which is m1x double dot plus k1x1 plus t, the tension, equals k1b sine omega critical times time. And then you're asked to solve for omega critical. On the other side, you have the same tensions that are acting there, and then you substitute it in, and you have two expressions with t. So you have two unknowns, t and omega critical. Rearranging everything, you get the tension is equal to m2 x double dot, x2 double dot plus k2 x2 divided by 2, and t is equal to 3.5, putting numbers in x2 double dot plus 170 x2. Putting one into the other, d into b, these two equations, you get this as your final expression. So now I have an expression that I can rearrange in terms of x double dot here. No longer have to deal with x2 double dot. And I have x1. So I end up with a standard sort of mx double dot plus kx equals a forcing. And the forcing is what I'm trying to solve for. And I end up with this expression right here. 99 x double dot plus 2020 x equals 540 sine of omega critical times time. Omega critical is going to be the natural frequency, substitute in all of those terms together, and I end up with 4.52 rads per second. Particle kinetics and kinematics, not really rigid body, chapter 8, and it's a focus on force vibration. Again, when you're dealing with these problems and you're looking at these types of questions, you're always looking at really the second half of the course. Really read carefully the sentences and try to make sure that you understand what's being asked for. We do try to make a lot of effort to make sure the questions are not confusing. And sometimes they still are, and we try to announce that during the lecture or during the exam. But we do try and do what we can. One thing I've noticed, and this is because you correct, when you correct the exams, you see this, draw your free body diagram. It does not save you time. It is not worthwhile writing all of this without drawing the free body diagram. No matter how clever you are, it's always easier to put the axes down, draw the free body diagrams, and always check units. And one thing I'd kind of add on the side of this, always use the right hand rule. Don't, no matter what we do to sort of flip things around, always use the right hand rule and then work from there. And once you do that, you're set. Okay. And thank you very much, and we'll talk again.